So hi everyone, and I would like to thank obviously the organizers for this invitation, and it's always a great pleasure to meet at this event. Um, so the work I'm going to talk about today is a kind of work in progress, in the sense that the document is not finished. So this is a first exposition of these results, and I hope to finish the document in a few weeks. So the motivation of this work comes from another work that we presented last year, which was with Jason Shooters and Joseph Peters about what is called the temporal spanners. And we had a kind of a conjecture that we wanted to test on many graphs, and possibly exhaustively on some families of graphs, and so came the ideas to try to create a generator for these graphs. Okay, so I will review quickly what is temporal graphs and what are the motivations, spanners, and then I will go into the detail of symmetries, generation, automorphisms, and stuff like this. Okay, so in this talk, a temporal graph will be represented in a very simple way, just as a labeled graph. Okay, so you have a graph. I don't know if you see my pointer, probably not.
Yes, we can see it right now.
Oh, you can see it. Great. Okay, so you have a normal graph. And in addition, we will just label the edges indicating at what time those edges exist. Okay, so for example, C and E have an edge at time 2, C and D have an edge at time 1 and 4, etc. There's many models. I don't want to get into the details here, and you may even have infinitely many times, an infinite lifetime, etc. But in this work, we consider a finite description of the graph and finite time and discrete time as well. Okay, so one of the main concepts in temporal graphs is probably that of temporal paths, which we call also a journey. So essentially what it is it's a form of reachability over time. Okay, for example, A can reach E by a sequence of increasing time edges. Okay, so like I can move here at time 3 and maybe here at time 4, and maybe here at time 4 if I allow for non-decreasing paths, or at time 5 if I require strictly increasing paths. Okay. So based on this definition of paths, we can define temporal connectivity. And we say simply that a graph is temporally connected if everybody can reach everybody through such a path. Okay. So for example, this graph here, you can check that it is actually temporally connected. There's a path, a temporal path from everyone to everyone. Okay, so temporal reachability is very intuitive, but it is also quite different from the static analog. In particular, it is non-transitive, okay? The fact that someone can reach someone else and this someone else again, does not imply that the first can reach the last. It depends on time. Okay, so this has caused a lot of studies lately, and in particular, it is known to make some polynomial problems typically become NP-hard in the temporal setting. So, okay, in this talk, I will focus on simple temporal graphs. And what we call here simple is essentially two restrictions. The first is that you have only one time for every edge, okay? Not two, not three. And the other one is that those times must be different locally to a same vertex, okay? So one of the initial motivation for this is probably distributed models in which you have, let's say, exclusive interactions between neighbor vertices. And so you cannot interact with several people at the same time, okay? This also makes, okay, one of my neighbors is currently making a hole in his wall. Can you hear is it
Only
disturbed?
very slightly.
Okay, great. Okay, so I will just have to make abstraction myself of the noise. Okay. So another motivation is a connection with edge-ordered graphs, which was brought to me by Victor Zamarev. And that's an old field of combinatorics in which you have quite similar models, although the questions are different. Also, a nice thing is that you don't need to distinguish between increasing and non-decreasing because everything is increasing here. And finally, this model can be shown to be useful to reduce more general models to it for some problems. Okay, in this talk, I will talk about how to generate these graphs and how to do it kind of exhaustively, even though they are in infinite number. Okay, so before that, just to remind you the motivation we had and that pushed me to write this generator and to work on it was a question about temporal spanners. So a temporal spanner is quite a natural concept. Let's say you have a graph, you're given this graph on the left, and the goal is to select a subset of the edges or of the labels in such a way that you preserve temporal connectivity, okay? And you want as few as possible. So it's kind of a spanning tree, except that you cannot always make it a tree, and actually you can almost never make it a tree. Okay, so there's a bunch of results in this literature. If we look at gossip theory, we already have some results. For example, the fact that you will always need at least 2n-4 labels. Okay, even though you were to choose the labels yourself. And okay, so in an explicit context of temporal graphs, we have this result where Kleinberg, Kempe, Kumar established that you may need, like, if I give you some particular graph, you may need to keep n log n edges. You cannot remove more unless you lose the temporal connectivity. And this was made even worse very recently, where Axiotis and Fotakis showed that you may even have dense graphs from which you cannot remove anything, essentially, which is kind of surprising because it means that there's no analog of spanning tree, even if we relax the definition just to be sparse. It does not even work in a guaranteed way. Okay, so that's quite intriguing. And also the computational complexity of finding a minimum spanner is much harder than in a static case, okay, as you can see. So that's what took us to this question, and we actually showed kind of the first good news in the story, which is that if the initial graph is complete, okay, if it's a temporal click, then you can always find a subquadratic spanner, like n log n sparse spanner. Okay. So that's our result. That was the starting point for this work. And the main question is that even though we proved n log n, we never actually found an instance that requires more than 2n-3. And that's yeah, sometimes we call it a conjecture, but we should be careful. I'm not sure that's a conjecture. It's an open question. Okay, so the initial motivation was to be able to generate all those graphs for a given n and to verify if they indeed admit to n-3 spanner. Okay, so now let's move into the generation problem. So first aspect of the generation is symmetry, because when you generate a combinatorial structure, you need to filter for symmetries. You don't want to explode in all the directions. So first, what is a symmetry? And there's a loose meaning of symmetry here and of equivalence that makes sense for problems of reachability. Like if you get these two graphs that you can see here, even though they are different, it occurs that their reachability is actually the same. Okay, in the sense that every journey in the first, every temporal graph, temporal paths in the first graph has an equivalent in the second graph. Okay, so they have the same sets of journeys. So there's different options to capture this equivalence. And a first option would be to have a local ordering locally to every vertex. You just order the local edges according to their times. And then if we look at the local ordering, then we can see obviously that these have the same reachability, those two graphs, because they have the same local ordering of the edges. So that's a very convenient property, but this is not the one eventually we worked with. Okay, so there's one that is actually that has more property for generation, which is just to compute a representative and to work directly on the representative. So what do I mean by this? I mean that both of these graphs actually have the same reachability than this one on the right. And this one on the right is essentially the minimal one that is equivalent to these graphs. Okay. So I will define by an algorithm more precisely what this means. But you see that all the three algorithms are the same, and we will consider this one on the right as the representative of the others. Okay, so working with representatives have many properties for generation that I will try to highlight in the following slides. Okay, in particular, the edge coloring induced by the time is very constrained and has very nice properties. Okay, now let me explain how to obtain such a representative from a graph. There's a simple algorithm to do this. So what you have to do is just to identify edges that are local minima. So for example, in the first iteration, you have this edge with 1. Possibly there could have been other edges and possibly with different times than 1. But here it's 1, and I will just relabel it with the minimum available time, which is also in this case 1. So it does not change. Then I identify again the local minima in the graph. So here 2 and 5 are local minima. By local minima, I mean that none of the adjacent edges have a smaller time. And then I relabel them with the next available time, which is 2. And then local minimas are these guys here. That gives 3, and then 4. Okay, and that's how I build the representative of a given graph. Okay, so what is this property about edge coloring that I was referring to? So first, you can observe that the coloring of the edges is proper, which means that no two edges which are adjacent can have the same color or time, it's the same. So this is already inherited from STGs in general. But in particular, when we work with the representative, we get the nice property that if an edge has label T, then there must be an adjacent edge with label T minus 1. Okay, so here I have, for example, this edge labeled 4. That means an edge which is adjacent to it should be labeled 3. And this one has a neighbor edge labeled 2, etc. Okay, and of course you must have this property, otherwise it means that the algorithm would have compressed it further down. Okay. Okay, and this property will prove to be very useful. Okay, it sounds a bit like a kind of coloring that is known to graph people. It's not exactly the same. And if some of you know the name of the coloring I said, I would be happy to know about it. Okay, so let's start to explore some of the features of graphs, in particular in terms of isomorphisms. So let's say you want to test for isomorphisms of two STGs. So you can do it in 2 steps. First, you compute the representative of both graphs, and then you test for classical isomorphisms of those graphs, okay, as labeled graph. Okay, so we already know that if your graph has properly edge-colored edges, properly colored edges, sorry, then we can test for isomorphism in polynomial time. In fact, the algorithm works on a larger class, and I will show you an ad hoc solution just for the case of properly edge-colored graph. So fix an arbitrary vertex on the left graph, for example, this one here, and we will just try to send it successively to every other vertex of the other graph. So here it will fail, then here it will fail, 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 and eventually maybe you find one. So these steps you can do as many as n, and each of them, that's the key point, each of these sending of vertices, you can test if it pass or fail in polynomial time. So why can you do so? Just because of the proper coloration of the edges, which will force a bijection between your local neighbors. Like I have an edge labeled 2 that leads to a neighbor. So that means that this edge with 2 must lead to the image of that neighbor. And so you can just recursively advance like this and check whether the isomorphism is valid or not. Okay, so isomorphism can be tested in polynomial time. And it's quite simple. Okay, in fact, you can use the same idea for automorphisms as well. So let's say you have a graph. You can test whether some of the, like you fix a vertex and you test if it can be sent to another vertex of the same graph. So here it's not the case, and then here it's the case. And just iterating like this, you can find all the automorphisms of your graph, which are at most n. Okay, in the case of edge-colored graph, properly edge-colored. Okay, so that's a very nice property. The problem is that when we generate the graph and when we will use this, it may happen that the graph is not connected, like the underlying graph is not connected. So in this case, for classical automorphisms, there's a trick that tells you that the complement of a graph has the same group of automorphisms as the graph itself. So usually we just flip to the complement and that's it. Here it's not the case because the complement is not a properly edge-colored graph. So I will not spend time right now. If it's of interest, you can ask the question later. But essentially what we can do here, we can isolate the components and then we test for isomorphisms among the components. Okay. And then we look for automorphisms within the components. Okay. And the sets of isomorphisms plus automorphisms gives you a set of generators for the automorphism group of that graph. So that's, if you must just keep one sentence out of this slide, is that we can compute efficiently a set of generators for the automorphism group of an STG, which is quite nice and which will be, of course, used in the generation process. Okay, so Eleni, how much time did I consume already?
You have about 3.5 minutes
okay,
left.
So let me move to the generation process. So the way we generate the graph is in this way. So we just split the generation according to times. And from a given graph, you just generate all the possible ways to add the next time. So it's not only adding one edge or one label. You may add many labels actually, but it's all the possible ways to add time 1. Okay. And then from each graph, you have all the possible ways to add time 2, etc. So why doing this? It may seem a bit unnatural to add several edges at the same time. The point is that it gives you a tremendous property for performance. So actually 2 properties. The first one is that rigidity is inherited, which means that if a given graph, let's say, for example, this one, if a given graph is rigid, which means it has no automorphisms, no non-trivial automorphisms, then its children will also be rigid, and the children of the children will also be rigid. Okay, this may not be the case if we were adding edges one by one, because you could then destroy symmetry and recreate it and redestroy it, like with static graphs. Here we have this just amazing property. Hi, are you here?
Yes.
Oh, sorry,
Yes.
my mic went off. Okay. Okay, so that's something that tells you that in the generation tree, once you reach a graph that is rigid, then all the subtree will remain rigid. That's a unique property that you don't have with static graphs. And in terms of performance, it will have a crazy impact because generating the children of a rigid graph is so fast that, I mean, much faster than when you have symmetries. Another one that is quite impressive is that dissimilarity is inherited. Like your children will have descendants that cannot be isomorphic to each other. So you don't have to check for isomorphisms down in the tree. Whenever it becomes different, it's forever. Okay. So those two properties actually have a huge impact on performance and imply that the generation of such graph is actually much faster than the generation of static graphs. Okay. Okay, so probably I should skip this part here. Here I explain how to generate the local children. So I give you a graph. What are the children? All right, so maybe just saying one thing. Due to the coloring lemma, the property I said before, you know that a new edge with a time, let's say 3, must be adjacent to edge of time 2. So for example, you know that the left graph will never occur. You will never have to generate such a graph, okay? Okay, so, and then the two cases for the generation are whether G has symmetries or whether it is rigid. So, okay, here that's the part I will not describe, just to say you compute the orbits of the edges using the generators that we saw before. And based on this, you can, let's say, generate uniquely all the children that are valid without having to test for isomorphisms among them. And if the graph is rigid, then that's where it is super fast because you just need to, okay, so you identify eligible edges. These are the ones adjacent to the highest time. And then you just enumerate all the possible matchings among those. And these are your descendants. You don't need anything else. So you just enumerate essentially these are the independent set in the line graph of the eligible non-edges. So this can be done with standard algorithms at a super fast rate. All right, so this is almost it. So these are just some numbers about the generation, and I would like to formulate as an open problem to count the number of STG representatives for n equal 8. It just seems to be out of reach because the number itself is so crazy. Like you can see how the number grow here. And about the temporal spanner, just to say, so these are the number of clicks and so far the open question has stand up to n equals 7. Okay, so it's not clear how it would go for n equal 8, but I'm actually very pessimistic on whether we can. I mean, we would never be able to generate all those graphs. Okay, just the number is so big, and yeah. Okay, I'm out of time, right?
Unfortunately.
Okay, so let me stop on that slide. So the conjecture is still open. We have verified spanners on click for n up to 7. That's not the main information of this talk, but just to make it a loop to the initial motivation. And yeah, okay, let me stop here. I don't want to